Very good evening, everybody, and welcome to the day 3 of ATAL sponsored faculty development program titled Innovative Micro and Nanotechnologies and Fundamental Principles, organized by the Department of Mechanical Engineering, Haldia Institute of Technology. So, you already have our eminent speaker today, Professor Amitabh Datta. So, let me give a briefing about Professor Datta's career. So Professor Datta is presently acting as a professor in the Department of Power Engineering of Jadavpur University. He has obtained his PhD degree from IIT Kharagpur in Mechanical Engineering. Professor Datta is a recipient of Alexander von Humboldt Fellowship in Germany in the year 2000 and worked at Lehrstuhl für Technische Thermodynamik in the University of Erlangen-Nuremberg in Germany. His research interests include combustion, atomization, energy, thermodynamic modeling, and application of CFD in reacting flows, microfluidics, and biological flows. He is a fellow of the Indian National Academy of Engineering and is a recipient of the Outstanding Teacher Award from the Government of West Bengal. He has held various administrative positions in his university and presently serving in the capacity of Director, Internal Quality Assurance Cell. With this short introduction, let us welcome Professor Datta for his expert talk today.
Okay, thank you very much for your introduction. I think everyone can hear me.
Yes, sir.
I will straight away go to my presentation and share the presentation with you. Okay. So, at the outset, I would like to tell all the participants that I am not really a person who works in the field of micro or nanotechnology. Though I have done some work in the area of microfluidic flow, CFD modeling of microfluidic flow, and in fact Abhishek did his PhD with me as one of his supervisor, and his topic was also in that area. But I will never claim myself to be an expert in the field of microfluidics or nanofluidics. So as the topic of this faculty development program is on micro and nanotechnology, I thought that as I worked in the area of combustion, I will take nano-sized soot precursor particle formation as the topic of my talk. In combustion, as you all know, particulates are formed, and those particulates, particularly they are called soot particles, they are really of nano size, means in the size of nanometer. So, but I will not again talk about soot particles as such. I will talk about particles which are even finer than the soot particles, and they are called soot precursor particles. And I will focus on a type of flame which otherwise looks like soot-free flame. These are called partially premixed flames, and we did some work quite extensively, I would say, with one of my PhD and a couple of my master students to find how these very, very small sized particles are formed and are emitted from this class of flame. So let me first yes. So let me first define what is flame. We see flame all around us in various different applications. For example, we see a flame in case of a candle. We see flame in our kitchen stove. Flame is there on Bunsen burners in the laboratory, in boiler furnace, in the combustion chamber of aircraft engine, or in the cylinder of internal combustion engine. Everywhere we see flame. Either we see or we perceive a flame. Now, what is flame? How do you define flame? Flame, by definition, is the zone of burning gases and fine suspended particles associated with rapid combustion. And it results in the evolution of heat and, in most cases, also light. So basically, flame is the zone of combustion and the zone of rapid combustion. Now, this term rapid is very important for flame. Rapid associates itself with some speed. So when you have combustion at high speed, with a high speed, then only you see a flame during the combustion. There are processes, burning processes, where the burning proceeds very slowly. Those are not burning with flame. Those processes are not even called combustion, we call them smoldering. For example, if you burn a cigarette, you see the cigarette burns, but burns very slowly. It takes quite a long time to complete the entire burning of the cigarette. Or sometimes you will find that dry leaves collected at the side of the road is burned, and you see that those leaves they burn rather slowly with the emission of smoke. Smoke comes out of the leaves, but you do not see flame. So flame you will only see when the burning takes place very fast, at a rapid rate. And during this burning process, there will be evolution of heat, because all these burning, these are oxidation reactions and they are exothermic in their character, so they liberate heat. And in most of the cases, you will also see light, and this light you will perceive in the form of some color, right? Now, the color of the flame can be different. It depends upon what are the particles present or what are the source of the emission from the flame, because the light that we see is a type of electromagnetic radiation, electromagnetic wave, and the color depends upon the wavelength of that electromagnetic radiation. Now, the wavelength of this emission again depends upon the cause of the emission, what actually emits the radiation. If you have soot particles present in flame, then you see the color of the flame to be yellow or orange, as you can see in case of a candle. A candle flame has soot particles present inside the flame. You may not find the soot particles coming out of the flame, but within the flame or inside to the flame, there are soot particles. These soot particles, as it comes out of the candle flame, burn in presence of air or oxygen in the surrounding, and therefore you do not see the soot particles to go up from the flame. On the other hand, there are other flames whose color is blue. Now, these blue flames that you see is devoid of soot. You do not have soot in those flames. Normally, the premix type of flame, I will come in the next slide, looks blue in color. Now, this blue color that you see in these flames is because of some radicals which are present in the flame. The radicals can be different. There are different types of radicals depending upon the components which are burning. So you may have CH radical, you may have C2 radical or OH radical, and all these different radicals emit radiation of different wavelength, and you see different color. For example, if you burn methane you know is CH4, then as the methane burns, there are lot of CH3, CH2 and CH radicals which are formed. All these class together as CH radical. And as the emission from the CH radical looks blue to our eyes, we see a methane flame to be blue. On the other hand, if you burn, say, propane as you know is C3H8. So when the propane gas burns, C2H5, C2H3, these type of radicals are formed. they class together as C2 radical. And these C2 radicals emit greenish blue color, a different shade of blue from what we see from CH radical. So therefore, when you burn propane gas, you sometimes see, again depending upon the concentration of C2 radicals, sometimes see the color of the flame to be a little different from the color of a methane flame. So basically, this emission that comes out of the radical is called chemiluminescence, and chemiluminescence is the reason, is the cause of different colors that we see in these type of flames. Now, flames can again be classified depending upon various factors. One important factor based on which the flames are classified is the mixedness of the reactant species. Reactant species are those species which react in case of combustion or in case of burning. So basically, fuel and oxygen or oxidizer, they are the reactant species. Now, based on the mixedness of the fuel and oxidizer, we can have different types of flame, primarily of two types, non-premixed and premixed flame. Non-premixed flame is that class of flame in which the fuel and the oxidizer, most of the cases oxidizer is air, because that air supplies oxygen, free oxygen it supplies. So air is the oxidizer in most of the cases. Now in non-premixed flame, the fuel and the air, they come to the flame zone, that means the burning zone, from different sides of the burning zone. For example, if I go back to the candle flame that is here, when a candle burns, you will find a pool of molten wax here at the top of the candle. With the radiation coming out of the flame, the wax melts and you find a pool of liquid wax here. Now what happens, this liquid wax, it rises along the wick by capillary action. And as the wax rises, it also evaporates. And the wax vapor comes out from the wick. And air or oxygen comes from this side, from the surrounding, from this side. So the wax vapor and the oxygen, they are never mixed beforehand. They come from two different sides, one from inside the flame and one from outside the flame to reach the surface of the flame, and then they mix there and burn. So this type of flame is called a non-premixed flame. And the non-premixed flame always looks yellow or orange in color because of the presence of soot particles present in these class of flames. Now there is another class of flame which is called the premixed flame, in which case the fuel and air are mixed together almost homogeneously, or homogeneously you can say, before the mixture comes to the zone of reaction. So the reactants, that means the fuel and oxidizer, they come as a homogeneous mixture to the flame zone in case of a premixed flame, and they burn there. The flame that we see in the combustion chamber of an SI engine, for example. In SI engine, you know that I think all the participants here are mechanical engineering background. So in SI engine, you all know that the fuel air mixture is prepared during the suction stroke, either within the induction manifold or within the combustion chamber. And when the spark is given during the end of the compression stroke, you already have a homogeneously prepared fuel air mixture present in the engine cylinder. And then as the flame propagates within the cylinder, the flame propagates in that homogeneously prepared fuel air mixture, or in other words, the homogeneously prepared mixture comes to the flame and it burns. So that class of flame is called premixed flame. Now, for any premixed flame of any fuel, there is something which is called flammability range. Flammability range is the range of air-fuel ratio within which you can sustain a premixed flame without any outside support. So, if the mixed air-fuel ratio is too high, that means there is a lot of air compared to the amount of fuel present in the mixture, or if the air fuel ratio is too low, then it will be outside the flammability range and you will not be able to burn a premix flame without any external support. Now, partially premixed flame is the third class of flame, which is also a premixed flame, but it has some specific characteristics with the reactant mixture. Now, let us understand what is a partially premixed flame. In a partially premixed flame is established with the interaction of a rich fuel air mixture and a lean fuel air mixture. So you know what is meant by a rich fuel air mixture, a fuel oxidizer mixture, and a lean or fuel oxidizer mixture. A rich mixture is a fuel oxidizer mixture, in which case the amount of oxidizer is more than the stoichiometric amount, while I'm sorry, amount of oxidizer is less than the stoichiometric amount. So basically, the rich fuel air mixture is rich in fuel. So you have more fuel than what the oxidizer can burn, ideally. And a lean mixture is a mixture where there is more than stoichiometric quantity of oxidizer or air. So when such a rich fuel oxidizer mixture and a lean fuel oxidizer mixture, particularly the mixtures outside the flammability limits, they interact and burn, then it produces a partially premixed flame. For example, let us consider a co-flow burner like this. Co-flow burner means there are two pipes, two concentric pipes, circular pipes involved. Let us consider circular, it can also be rectangular. So there are two concentric pipes. So this is the inner pipe and this is the outer pipes, and thus this region is the annular region between the two pipes. Now suppose you supply a rich fuel air mixture through the inner pipe and only air, or a lean fuel air mixture through the outer pipe, right? So either air as I have shown here, or lean fuel air mixture from the through the annulus between the two pipes. Now then what will happen? Now this mixture is rich. This is a fuel air mixture, already prepared fuel air mixture, but this is rich. So when you ignite, this produces a premixed flame here, but as the mixture is rich, that means there is insufficient quantity of oxidizer present with the fuel, the flame will not be able to completely burn the fuel. There will be incomplete combustion because of the because of less amount of oxidizer. And due to this incomplete combustion, there will be products which are still flammable. Say, for example, hydrogen or carbon monoxide or other products will remain in the gas that comes out through this flame. Now, when you are supplying air from the surrounding, these incomplete combustion products can further react or burn with the supply of this air, and that produces another flame on the outside. This flame on the outside is not a premixed flame, it is a non-premixed flame, because the fuel that is burning in this flame is coming from inside as the incomplete combustion product of the inner flame. And this fuel they burn with oxygen coming from outside. So the fuel and the oxygen they from different sides of the flame and burn here in the flame. Thus, this other flame here, you see two flames. You see this is a double flame structure, as I have shown here. You see, this is the inner flame and this is the outer flame. Now you can see this flame is a propane flame, and you can recognize the color of this inner flame, which is somewhat greenish due to due to the burning of propane and due to the abundance of C2 radical in the flame. So the picture here clearly indicates that there are two flames. This is the inner flame and this is the outer flame. The inner flame is a premixed flame, a rich premixed flame that cannot completely burn the fuel, and any incomplete combustion product which is further burnable or further combustible, comes out of this inner flame and burned with air coming from the surrounding to complete its combustion at the outer flame. So this is what is called a two flame or double flame structure. You can even have a triple flame structure, as you can see here. So you can see here that there are three flames. This is the inner flame, this is the middle flame, and this is the outer flame. And such triple flame structure can be seen when a rich mixture interacts with a lean mixture. So you have this inner flame as a rich premix flame, this outermost flame as the lean premix flame. Now the rich premix flames produces incomplete combustion products which are further combustible. Lean premix flame burns the fuel completely. As the mixture is lean, you have extra oxygen, so some more oxygen will come out with the gas, and this oxygen and the fuel coming from inside form the non-premix flame in the middle. So thus there are three flames here, as you can see here. So this is called a triple flame. Now these type of flames are called partially premixed when the mixtures are such that they are outside the flammability limit of the fuel. Now, okay, so now these partially premixed flames, they have different characteristic features. Firstly, this shows multiple reaction zones. A double flame shows two reaction zones, a triple flame shows three reaction zones. So there are multiple reaction zones. And these reaction zones are spatially separated, but they are synergistically coupled. Now, synergistically coupled means, as I am telling you, that this flame here burns with a rich mixture outside the rich flammability limit. That means this is too rich compared to the limit up to which a premix flame can burn. Then the question is, how does this rich premix flame survive with a fuel air mixture that is outside the flammability? Now this rich premix flame can only survive due to the existence of the non-premix flame on its outside. You will not be able to burn a rich mixture richer than the rich flammability limit in an enclosed space without any external support. Here, you can establish the rich premix flame only due to the coupling with the non-premix flame that you have here on the outside. So there is a transfer of heat, there is transfer of some radicals from the non-premix flame that helps the rich premix flame to survive even when the mixture is outside the flammability limit. This is what is called synergistic coupling between the two flames. One of the most important advantage of partially premixed flame is that as you can have this rich mixture outside the flammability limit, there is no chance of flashback within the burner. So thus the partially premixed flame is much safer in their characteristic compared to the normal premixed flame. And secondly, the partially premixed flame is much more environment friendly in comparison to non-premixed flame, or sometimes even in comparison to premixed flame. It is more environment friendly compared to non-premixed flame because there is very little formation of soot or almost no formation of soot particles in case of a partially premixed flame. If you do not maintain the richness of the mixture too high, right? So these are some of the advantages. Now, what are the applications of partially premixed flames? Are they really important so that we discuss largely on them? Yes, they are having a lot of applications in Bunsen burner, domestic gas burner, lifted flame, turbulent flame, and stabilization of a non-premixed flame is also through a partially premixed flame. So there are a lot of applications for which partially premixed flames has found a lot of interest by the combustion researchers. If you look at a standard LPG cook stoves that we use in the kitchen, right, a domestic cook stove, how does it function? The food stove functions following Bunsen-Burner principle. Now, what is the Bunsen-Burner principle? In case of a Bunsen-Burner, if you remember, you have used Bunsen-Burner in your chemistry laboratories maybe long time back. But if you remember, you will see in a Bunsen-Burner there is a nozzle through which you supply the fuel gas, and the nozzle is open in a tube which is having an opening on its periphery, and as the fuel gas comes out through the nozzle with a high velocity, it entrains air through that opening, and that results in the formation of a fuel air mixture. Now, if you just turn your stove and look it from the bottom, you will find something like this. You will find that the LPG hose is connected here, and it goes through this cock, right? Which is nothing but a valve, you can say. And if you look after the valve, you will find a mixing tube, right? A tube in which there is a nozzle and there is an opening here at the tip of the nozzle. So the fuel that comes through here, when you open the cork, the fuel comes through the nozzle, and it comes with a high velocity. Now, this fuel jet entrains air from the surrounding through the opening that you have here on the mixing tube, right? And thus, you have fuel and air together coming through the remaining part of the mixing tube. So they mix, and they also mix in the burner, and then you have the burner top like this, where with large number of small holes. So the fuel air mixture which has been prepared here comes out through these holes, and the amount of air that is entrained as the fuel comes through the pipe is not of stoichiometric quantity, much less than stoichiometric quantity. Thus, the fuel air mixture which is prepared here is really a rich fuel air mixture. And this rich fuel air mixture, as it comes through the holes and you ignite the mixture, you establish premix flame, partially premixed flame on the top of each of these holes. So if you look at the flame, it looks like this. You see these small flames, premixed flames, having very high, quite high fuel air ratio. So they are really a very rich premix flame established on each of the burner, each of the port on the burner top. And as the fuel is not completely burned in these small flames, there are unburned products, and these unburned products, as it comes out, it encounters air from the surrounding. Air comes from the outside here, and there is, you know that there is a small hole here at the middle of the burner top. Air also comes through that hole, and that establishes the non-premix flame. So you can see this flame here, this flame, and this flame here. These are the non-premix flame, where the unburned gas, incomplete combustion products from this premix flame burn with either air coming from the surrounding or air coming from the middle. So this is the structure of the flame. And in all these flames that you see on each of the burner port, they are basically partially premixed type of flame. Now, you can design the burner top with various different hole structure, right? We in fact did that. We drilled hole of different diameters, keeping the total area of the opening the same, so that the velocity of the gas coming out remains the same because they come out through the same area, but the diameters are different. As you can see here, these are large number of holes but small in diameter, while this is larger diameter holes and small in number. So if you consider these A, B, C, and D 4 burners, burner tops, for A, this is the standard burner, where the hole diameter is about 1.8 millimeter, and there are 2 holes on the outer side and one row on the inner side, right? So this is the burner B, where the hole diameter are smaller, 1.1 millimeter, therefore larger number of holes, and in 5 different rows, 2 on the inside and 3 on the outside. Then in this case, the Warner hole diameter is 2.2, so larger diameter hole, smaller in number. And this is a case where the diameter is the same as A, but the holes are drilled in a tilted manner, giving a swirling motion to the flow. So in all these four cases, we tested on a domestic stove, and we see different types of flames. And we also measured the efficiency of the stove with these different types of burner tops, and found some, not much difference, but a little difference, about 1% difference in efficiencies in some cases. But I'm not interested about the efficiency in this top. I am more interested about the type of flame, the color of the flame, and the soot particles emission from this flame. So if you have to look into the soot particles, you have to run the flame for some time, and we continued with the flame for 20 minutes for each of these case. And after 20 minutes of running, we found that for case B, a lot of soot particles are deposited on the top of the burner. So the burner became like this, black. Now, these soot particles are not good for cooking. If they deposit at the bottom of the utensil, that becomes, more difficult to clean the utensils, and all such things happen. But our interest is to see under what condition or for what reason these soot particles are formed. So let us now look on the particulates which are formed in case of combustion. Now, combustion generates different types of pollutants, and particulates are one such type of pollutants generated in combustion. Now, particulates in combustion can either be in the form of ash or in the form of carbonaceous particles. Now, ash is the incomplete combustion, not incomplete combustion, I would say. It is the product. It is the product which is left behind once you completely burn the fuel. And we see ash to form mostly when you burn coal, because coal contains a lot of ash, and the coal ash are basically different types of mineral matters in the form of oxides of acidic or basic natures, alkaline nature. And as you burn coal and the coal gets completely burned, you are left with these ash particles. So such ash particles, they can be very fine depending upon how, in which form you are burning the coal. So when you are burning the coal in pulverized form, very fine ash is formed. And in a thermal power plant, when pulverized coal is burnt, most of the ash is so fine that they are carried with the flue gas and form the fly ash. And you have to separate out that fly ash from the gas before leaving the gas into the atmosphere, because otherwise the ash will pollute the environment. So ash is one type of pollutant. Now, when you burn gaseous fuel like methane, propane, LPG, or whatever, then almost no ash is formed, because you do not have any such mineral matter present in gaseous fuel. Even when you burn liquid fuel, for most of the cases, when you burn, say, gasoline, or when you burn diesel, you will not have any ash formed. Of course, when you burn heavy fuel oil, a little amount of ash, very little amount of ash can be formed, but otherwise, the liquid fuel burning is also devoid of any ash. But gaseous or liquid fuel burning can form carbonaceous particulates. Carbonaceous particulates are those particulates which are having carbon in them. And soot is the most common form of carbonaceous particulate which we see. Now, what is the constituent of soot? The constituent of soot is not entirely carbon, but you also have some hydrogen present in soot, but it is mostly carbon. Mostly, more than 90%, 94, 95% is carbon. And this soot is normally present in agglomerated form. So very, very small size particles, they join together to form soot particles. If you look under a electron microscope, it looks like this, right? So you can understand there are small particles joined together in the form of a conglomerate to form soot.
প্রথমে ভর্তি হতে
Now,
আমি ইয়ে হয়েছে
even when you burn gaseous fuel, so say for example you are burning LPG in your kitchen, and that gaseous fuel, when it burns with it burns in air, which is also gaseous, forms these solid particulates in the form of soot. Now, how is these soot particulates are formed, and what is the size of these particulates? Now, the particulates in the form of soot are formed through a very complex chemical process in which the formation starts with components like carbon monoxide, carbon dioxide, oxygen, and hydrogen, etc. Now, these molecules, they join together, and after some time, under certain circumstances, they form an aromatic ring like this, like a benzene ring. Benzene ring, as you know, is the simplest type of aromatic ring. So these aliphatic compounds, they some under some particular condition, they join together to form these aromatic compounds. Right. This is what is called aromatization of molecules. Now, once this aromatic molecule is formed, further joining of molecule takes place on the side of these molecules, aromatic molecules, and they grow together. They grow. So from one ring they become two ring, from two ring they become multiple ring. So this is what is called polyaromatic hydrocarbon, when you have a large number of aromatic rings joining together. Now, as they grow, their molecular weight increases, and after certain time, when the molecules become sufficiently grown up, they cease to behave like molecules. They start to behave like particles. There is significant characteristic behavior of the molecules and the particles. Right? Molecules, they follow kinetic theory, and kinetic theory of gas molecules, where they can move around randomly in gaseous form. But particulates do not behave like that. So when the molecules, as they grow up, become significantly large in size, in terms of, number of rings, in terms of their molecular weight, they cease to behave like molecules and they start behaving like particles. And from that point, the particulate nature of the constituent starts. So the beginning of particle formation begins, right? So this is the beginning of the particle formation, and then these particles further grow together. They grow together because of conglomeration, because of joining, because of coagulation, surface growth. So surface growth and coagulation are two typical process by which coagulation means when two small particles join together to form a larger particle. Surface growth, when further molecules add on the surface of the particle to increase its size. So these are two different processes altogether. And because of these processes, because of surface growth on the molecule, and because of coagulation of molecules to form larger molecules, the molecules grow in size, and finally they become like an agglomerate and result in the formation of soot. So when the soot particles are formed, the size of the particles remain anything between, say, 20 nanometer to 100 nanometer. So they are really of nanometer size and very small in their size. Now, these small nanoparticles have various harmful effects on the environment, harmful effects on the human and animal bodies, right? Now, the most harmful effect that these small particles can do is the deposition in the lung, in our pulmonary system. So when you inhale air, the particles get uh, into the pulmonary tract, right? And the particles are of various size. The particles which are present in air, it's not only soot particles. There are other types of particles. There are dust particles. There are ash particles, many different particulates can be there in atmosphere, and these particulates are normally classified in terms of PM size, PM10, PM2.5, PM.1. You know about these nomenclature. PM10 are those particles whose aerodynamic diameter is less than 10 micron. So these are quite large. I mean, small, but with respect to the particles, these are quite large. So then PM2.5 are those particles whose aerodynamic diameter is less than 2.5 micron, and PM.1 are those particles whose aerodynamic diameter is less than zero point 0.1 micrometer. Zero point 0.1 micrometer means 100 nanometer. So most of the soot particles, they are of PM.1 class. But of course, some soot particles can exceed 100 nanometer in size, and then they will go into the PM 2.5 class. Now, these different particulates which are present in air, as they get into the pulmonary tract or pulmonary duct, can reach deeper into the duct, and when they are very small in size, they can further get into the alveoli, which are at the extreme position of the duct, and across whose wall the gas transfer takes place. So you know that at the tip of these bronchioles, you have these small alveoli, and across the wall of the alveoli, oxygen and carbon dioxide transfer, by which the pulmonary system and the blood system, uh, they exchange the gas. Now, when the particles are very small, for PM.1 size particles, the particles can even cross the alveolar barrier. So, in such case, these small particles can even get into your blood system, and then they will circulate through this circulatory system of ours, of our body, and get into the every part of the body. So that is very, very harmful, and can cause various different diseases in the body. So thus, these very small soot particles are really harmful to our health, and they are also harmful towards in the environment, because they affect the Earth's radiation balance by backscattering of the absorbing radiation, and thus they lead to global warming and increase the temperature of the Earth. So thus they have both harmful effect on the environment and also on the human and animal health, and you have to control, right? You have to control the emission of these nanoparticles from any type of flame. Now, if you now look at the partially premixed flames, the non-premixed flames are very sooty. The non-premixed flames, where, as I have told you, the fuel and oxidizer come to the flame from two different sides to burn, they are particularly very sooty, and look like orange or yellow in their color because of the emission by the soot particles at the temperature of the flame. Now, why are they sooty? They are sooty because, you see, this is a non-premixed flame. The burner here only supplies fuel, and the fuel burns with oxygen coming from the surrounding air. So the fuel comes from inside the flame, and oxygen comes from outside the flame to mix at the flame and burn there. Now, in this case, inside the flame, you do not have any oxygen. So what happens? The fuel that comes to the flame due to the high temperature, the fuel that comes through the burner due to the high temperature, due to heat transfer from the flame, they pyrolyze. The fuel pyrolyze, and they break into smaller molecules, and then those smaller molecules join together to form the soot particles. So that is the reason why you have soot formation, lot of soot formation in case of non-premixed flame. In case of premixed flame, you also have oxygen present with the fuel coming through the burner. So the chance of the pyrolyzed particle to join together is not there, because they find oxygen and get oxidized, right? So thus for a premix flame, you will not have a lot of soot particles present in the flame. But that is there in a non-premix flame. Now, as you go on adding small and small amount of air, or little amount of air, go on increasing the amount of air. You see, this is a parameter called equivalence ratio. And as this equivalence ratio gets lower, that means you are adding more and more air with the fuel, or oxidizer with the fuel. But they are still rich. It will remain rich till phi is 1. Okay. So all these are rich cases. Rich fuel air mixture coming through the burner. But you can see, as you go on adding air with the fuel, the amount of soot formation becomes less, and the flame height also becomes less. And coming to this case, when phi is 3, there is also a blue tinge in the flame, right? And you can now separate slowly start seeing the separate non-premix flame from the premix flame. So thus, when you have a partially premixed flame with air coming with the fuel through the burner, the amount of soot formation is less. But does it mean that there is no particulate? You can find, say for example, in this case, these are all partially premixed flame with rich mixture coming from through the burner, and there is no orange or yellow color in these flames. So does it mean that there is no particulates in these flames? That was the question. There is no soot. That's fine. But is there any particulate present in this flame? That was the question which we tried to get the answer in this particular research which we conducted sometimes back. So does it mean that a blue flame is devoid of any carbonaceous particle? Right. Does it mean that in a blue flame there is no carbonaceous particle present? That was the question which was asked. Okay, so let me stop here and ask the participants if they have any question up till now. Then we may discuss on that and can further proceed. Do you have anything to ask on what I have told so far? Okay. I mean, can you hear me?
Yes, sir.
Okay. All right. So if you have no question, I will further proceed.
Sure,
sir. Sure.
Yes.
Sir, I have a question. When we have already seen that at the time of oxyacetylene gas welding, we have seen different types of flames.
Right.
And they have also the different types of colors.
Right.
So, in which group they are?
Yes.
They are also partially premixing or not?
Right. An oxyacetylene flame is a premix flame. Okay. An oxyacetylene flame is a premix flame. You can vary the amount of oxygen in the flame, and as you vary the amount of oxygen, you find the color of the flame to change because of the variation in the concentration of the radicals present in the flame. Acetylene, it is C2H2, right? Acetylene is C2H2. It is burned with oxygen in the flame so that the temperature can be high, right? So when C2H2 burns, you will have some C2 radical and you will have CH radical in abundance. So therefore, when you have sufficient amount of oxygen given to the flame, to the mixture, you will find the color of the flame to be blue. But if you reduce the amount of oxygen, then you find the color to be a little greenish because of more amount of C2 radical in the flame, right? Now, if you do that, if you reduce the oxygen quantity significantly in order to get a green type of flame, you will not find the temperature to be high because as you are burning, at least in the inner flame, because the mixture will be a little richer, right? So you have to adjust your amount of oxygen in such a manner that the temperature of the flame can be the highest, and you can either weld or you can cut or whatever you like to do. Okay.
Okay, okay, sir.
All right. So let us now proceed to this. Now, up till now we were talking about soot, but there is another class of carbonaceous particulates that can be found in flames, and those are called soot precursor particles, or they are also sometimes called young soot particles. So these soot precursor particles or young soot particles are smaller, even smaller to that of soot, and they have less number of aromatic rings in their structure. They are smaller because they have less number of aromatic rings, and as they have less number of aromatic rings, the hydrogen to carbon ratio in these particles are found to be somewhat greater than what is obtained in soot particles. So while in soot particles you will find the hydrogen to carbon ratio as 0.1. 0.1 hydrogen to carbon ratio means there is 90% carbon and a little around 90% carbon, I would say, and 10% of hydrogen. While in these nano-organic carbon or nano-organic carbon particles or young soot particles or soot precursor, they are called by different names. The hydrogen to carbon ratio is 0.4. So you can understand that the hydrogen is much larger in quantity in these particles. And they have different other properties. So, for example, these nano-organic carbon particles are more hydrophilic, while soot particles is generally hydrophobic. That means nano-organic particles, they have an affinity towards water. So if you pass a gas containing soot particles through water, the soot particles may pass through water without getting dissolved in it. While if there are nano-organic particles, nano-organic carbon particles in the gas, then when you pass it through water, the nano-organic particles will suspend in or dissolve in water, and they get collected in water. So that is also not good, because the water will get polluted with these nano-organic carbon particles. Also, the optical properties of the soot particles and nano-organic particles are different. Soot particles, they absorb or emit radiation over a range between UV to visible. And that is why when you have soot particles present in a flame, due to emission of visible radiation, you see particular color from the soot particles, the color which is orange or yellow, right? But nano-organic carbon particles, they absorb or emit in the UV range, which you cannot see through your eye. So you cannot trace the color through this nano-organic carbon particle emission. They also emit, but they emit in UV range, and that is why you cannot observe or you cannot perceive the presence of nano-organic carbon particles from their color in the flame. So that is a very important difference, and that is the reason why even if nano-organic carbon particles are present in blue flames, you cannot perceive them just by seeing. You cannot see the color of the radiation emitted by these nano-organic carbon particles. But if they are emitted into the atmosphere, as they are very small in size of 10 nanometer or even less, they are really very harmful. They can get into the deepest part of your body and can cause harm to your body. These carbon particles can deposit into your body. So that way, these are even more harmful than the soot particles. So what we did an experiment. Let us get into this figure. Yes. So we did an experiment where we used a burner. This is the burner here, and we established a partially premium temperature of LED or propane on the wire, and then with help of probe, we suck the gas from different position of the flame. Right, there is a vacuum pump by which we suck, and this is a the probe was designed in a manner that the suction of the gas from the flame could be done isokinetically. Isokinetically means it does not change the chemical condition of the flame. It does not change the composition of the gases present in the flame. Now, this isokinetic sampling from the flame is done by this very small probe. The probe has a very small tip, sharp tip, so that it does not disturb the flame when you insert the probe inside the flame at different position. Now, then what we did, we passed this gas through a test tube that contains water. Right. So when the gas is passed through the test tube containing water, if there are nano-organic carbon particles in the gas, you are sucking the gas from the flame. So if there is nano-organic carbon particle in the flame, then that will also be in the gas. And when you pass the gas through water, those nano-organic particles being hydrophilic, they will remain in water. They will not pass through. And then you can use that use sample from that water to test and see whether the nano-organic particle existence of nano-organic particle is there or not. So that will establish whether the nano-organic particles are present in the flame or they are not present. And the tests can be of various types, mostly optical tests using uh, different interaction between light and matter is done either by absorption spectroscopy or fluorescence, or if you want, we did measure the size of the particles, nano-organic carbon particles, and we used a technique called dynamic light scattering technique, DLS, and we also did some measurements with emission spectroscopy. Now, what is done in absorption spectroscopy, light is passed through the sample, and depending upon the constituent of the sample, light over a particular wave band is passed through the sample, and depending upon the constituents present in the sample, wavelength of light of certain wavelengths get absorbed, right? And then if you find out the wavelength of the emitted light that comes out of the sample and compare it with the source wavelength, you can find out the absorbance, right? So you can find out the wavelength at which the light is absorbed. And then you can calculate the absorbance. The absorbance is defined in this manner: the log of I0 by I. I0 is the intensity of incident light, and I is the intensity of the light that comes out, that is transmitted through the sample. So this absorbance is a product of epsilon, which is the molar absorptivity, L, which is the length of the sample, and C, which is the concentration of the absorbing constituents present in the sample. So concentration of solute, because you use a solvent in which you give the sample. So the sample acts like a solute. So C is the concentration of the solute. So that means from the absorption spectroscopy, you can measure the concentration of the solute which you are adding into the sample as which you are adding into the solvent as sample, right? So when we did that, all right, let us come to the results later. The other technique which we used is the fluorescence spectroscopy. In fluorescence spectroscopy, this is another optical measurement. In this, what is done, the sample is illuminated with a light of certain wavelength. Now, this light, when the sample is excited with this light, the electrons of the outermost orbit get excited and they go to an excited state from their ground state. Now they cannot remain in this excited state for long. So what they do, they emit some wavelength and try to come back to a more stable state. Now this emission that that comes out from the sample, from the molecules, when they get excited and then try to come back to a more stable state, is what is called fluorescence. Now the the wavelength of the fluorescence depends upon the depends upon the molecule, depends upon the sample, because these states are all different for different molecules. So the gap between these different states are always different for different molecules, and therefore the wavelength of the emitted sample or fluorescent sample is an indicator of the molecule which is present in the sample, right? So nano-organic carbon particle, they have a typical fluorescence wavelength, and if you check whether you get fluorescence of that wavelength or not, gives you an indication whether nano-organic carbon particle are present in the sample or not. So what you do, you use a light source and then you select particular wavelength from that light source to illuminate or excite the sample placed in the sample chamber. You have to select the wavelength so that the molecules can be properly excited and the electrons can be taken from their ground state to the excited state, because these energy levels are all very different for different molecules, right? So for the particular molecule that you like to test, there will be a particular wavelength by which you have to excite, and this selector selects that particular wavelength to excite the sample. Now as the sample gets excited and the electrons go to the excited state, they as they come back to their more stable state, they emit some radiation, and that radiation is again of a particular wavelength. So the detector detects whether emission of that wavelength is coming out of the sample or not, or in other words, the detector detects at which wavelength the emission comes out from the sample. So if you have a matching wavelength compared to the molecule that you want to test, you will know that that particular molecule is present in your sample. So this is how a fluorescence spectrometer works. And then we also did the size measurement of these nanoparticles using a technique called dynamic light scattering, where the diffusion coefficient of the particular sample is tested, and this diffusion coefficient can be related to the radius of the sample, radius of the particles, and from there you can find out the radius of the particles which are there, right? The particles are all moving, the molecules are moving, the particles, these are the red ones, they are also moving, and depending upon the diffusion coefficient of these molecules, how they diffuse, this Brownian motion is only diffusion, and depending upon that, you can find out the size of the particle from this particular measurement technique. Okay, so what we did, we establish a partially premixed flame like this, and then we take our probe at different points within the flame in the region where the color of the flame is blue, right? So normally it appears that as the color is blue, you do not have soot particles present there. Soot is formed much later, say for example in this region. So probably there will not be any particulate in this region. But we when we tested the sample under these different optical measurement technique, we found signals which are indicator of the nano-organic carbon particles. So this peak that you see here is typical for the nano-organic carbon particles. So this is an earlier work where ethylene air premix flame was used, and they found a similar type of absorption spectra as we found here for different position from different position of the flame. So you have typical peak here as well as here 266 nanometer. This one is 266 nanometer. They also obtained similar peak in this region, and this is an indicator that at these positions, 3 millimeter, 6 millimeter, or 10 millimeter height and 4 millimeter radial distance, 4 millimeter radial distance, there is nano-organic carbon particle present in the same. Yeah. No soot, because you see the soot particles absorb or emit in the visible range, but there is no signal in the visible range, right? 400 nanometer and beyond, there is no signal uh, uh, that we receive. But the signals are only there in the UV range, less than 400 nanometer range, and at typical wavelength, which are for NOC particles. So similarly, when we did the fluorescence measurement and obtained the fluorescence images, there also we see the fluorescence to be at typical wavelengths for NOC particles as observed by others. So thus, the when we excited by 260 nanometer, we obtain fluorescence spectra or fluorescence peak at these particular wavelengths, which are typical, or this particular wavelength, which are typical for NOC particles. So these are all indicators of NOC particles present in the flame. So these are some other results. Let us keep this. This is again for different absorption spectra for different position, different radial position, 3 millimeter, 4 millimeter, different radial position at the same axial height. And this is for axial height of 6 millimeter. And you can see in all these cases, there are presence of these typical peaks, which indicate the presence of NOC particles. So thus, even in the blue region of the flame, where soot particles are not normally present, right? That is the reason why the color is blue. If you have soot particles,
one thing.
yes.
So it is observed that all the peaks are obtained at lower wavelengths.
Yes, lower wavelength means in the ultraviolet range.
Okay. In the previous slide also, the spectrums that you have shown, yeah, it's all in
Yes,
the lower.
these are all in the ultraviolet range. These are
Okay.
none of this is in the visible range. Now, if you have soot particles emit radiation in the visible range, for which you see the color of the flame as orange. Means orange is a wavelength in 400. I mean, it is around 620 nanometer or so. So, soot particles, if it is present there, you will find emission spectra or absorption spectra. Basically, the wavelength at which the molecules emit, it absorbs at the same wavelength. Okay, when you irradiate or illuminate the molecule.
So,
Now,
is there any reason why it is only in the lower range of wavelength?
it is in the lower range because there is no soot particles. I mean, the nano-organic particles which are there in the sample, they absorb in this wavelength range only.
Okay.
Right? These are the typical wavelength range at which the nano-organic particles absorb. The soot particles absorb light in the visible range. So when you illuminate you see here in the absorption experiment, we illuminate the sample with a tungsten lamp and a deuterium lamp. This is a tungsten lamp and this is a deuterium lamp. And the wavelength for these two lamps span from UV to visible range. So you have a very wide range of illumination, but the absorption that you get is only in the UV range, right? Not in the visible range. The visible range light passes through. It does not get absorbed. Now, if you have soot particles present in the flame, and if you illuminate, irradiate, or you whatever you call, with visible light in that range of orange or yellow color, you find the soot particles to absorb, right? Now, here it is not so because the nano-organic particles do not absorb in the visible range. Nano-organic particles only absorb in the ultraviolet range, less than 400 nanometer, much less than. And the typical wavelength at which they absorb is 266 nanometer or this 200 nanometer or so. So that is what we also got. I mean, these were reported by other researchers from different other type of flame, pre-mixed flame. In partially pre-mixed flame, we also got the same result, right? So that indicates that the particulates which are present in the blue region of the flame are not, I mean, there are particulates, and those particulates are nano-organic particulates. So it is an important observation in the sense that sometimes we think that when you have blue flame, there is no particulate emission from flame, but probably this is not entirely correct, because such nano-organic carbon particulates may be there in these blue flames. And those particulates being very small, very, very fine, less than 10 nanometer, can even be more harmful than uh, soot particles. Soot particles are, of course, very harmful, but these are even more harmful because they can penetrate much deeper into your body. Okay, so we also did there is an equation which is called Tauk equation, by which you can do some calculation and can find out how the number of aromatic rings present in these structures, right? In this particular structure. And we did that, and we found that the particulates which are present in these samples, they are having 2 to 3 aromatic rings or 7 to 10 aromatic rings. So two different classes we found, two different band gaps, and these two band gaps are they correspond to two different types of particulates, one with 2 to 3 aromatic rings. So you can understand the soot particles have have much larger number of aromatic rings present in them, right? Maybe around 50, 60, or even more than that. But these particles, this class of particles, they are at the early time of soot formation. So that is why they are also called young soot particles, and they have really very small number of, very fewer number of aromatic rings in their structure. So that makes these particles smaller in size, and that makes their molecular weight also very small, much lower than that of soot particles. And these are the size measurements which we got from DLS. And you can see the size for different position. Peak size is up to 6 nanometer for this particular position, to 10 nanometer, 10 millimeter height position. While for these are even small, 3 nanometer or 2 nanometer, up to that. And also measured the size using transmission electron microscopy, TEM. And TEM measurements also give the size to be very small. But you see, there will be some difference between the TEM measurement and the DLS measurement, because when you do DLS measurement, the sample remains in a liquid, right? Suspended in a liquid. And therefore, the molecules, if they are spherical, can remain as a solid. But when you have to drop the sample on a solid surface, on a grid, and when you drop the surface on the grid, the surface can spread if the molecule is in liquid form. If the particulate, not molecule, particulate, these are all particulates. If the particulate remains in solid form, then they will remain solid. They will remain as a sphere when they are dropped on the solid surface. But if the particle remains as a liquid particle, then they will spread. And if they spread, the size, if you try to measure the diameter will appear bigger, right? The diameter will appear bigger. Do you understand what I'm saying? I mean, if you drop a liquid droplet on a solid surface, when the drop is liquid, then by putting it on a solid surface, it will spread. And if it spreads, and if you look from the top to measure its diameter, you will see the diameter, or the diameter will appear bigger than larger than the actual diameter of the drop. But if it is a solid, it will not be so. I mean, if it is a solid sphere, then by putting it on the solid surface, it will remain like a solid. And if you measure the diameter from the top, you will only get this diameter. Now, when we drop this nano-organic carbon sample on the TEM grid and measured the size, we found the size to be somewhat greater than what we have measured using DLS. And that established that these nano-organic carbon particles probably do not remain in solid state, but they remain in liquid state. Right. So as they as the particulate formation occurs, and from the gaseous molecules they become larger, they join together to become larger and become solid soot particles. In between, they pass through a liquid state where they are particles. They convert from the gaseous molecule to particles, but the particles do not behave as solid particles, they behave as liquid particles. So, thus, these nano-organic carbon particles, which we are talking about, may also behave as liquid particles, liquid droplets of very small size, for which, when you measure the diameter using TEM, you get a somewhat larger diameter than when you do it using DLS.
So why this is so? The phase change does not take place, but at a transition between solid and liquid, it behaves like that.
Yes, I mean when
So there is
the
not a
formation
phase
begins.
change from solid to liquid, but at a transition in between solid and liquid. That's why the variation in
Yes,
the
when the change occurs from the molecular level to the particulate level,
okay,
right, by the growth of the particle, growth of the molecule. I mean, by
right,
the growth of the size of the molecule, the
okay,
molecules grow in size by joining together,
right.
right? And as they become larger and larger, they cease to behave like a molecule, right? They transform to particulate. And when they become significantly large, they become solid. But before going there, they cross a region, they cross a phase where the size is significant, I mean, quite large, so that they do not behave like molecule, but they are not even solid. They transform through a liquid
Neither
phase,
solid nor liquid.
neither solid nor gaseous.
Okay,
They remain in a liquid like
okay,
situation,
okay, okay,
because
okay.
of which when you drop on a solid surface, it spreads, and when it spreads, you see this and you measure. See what happens in transmission electron microscopy. You measure with the help of electron camera from the top, and the size becomes larger because of the spreading of the molecule. So we also did the measurement at different equivalence ratio, I mean different air fuel ratio of the mixture. And there also we found such nano-organic particles from the blue region. So we sampled from this position, and this position, all in the blue region, and found the particulates to be there of very small size. So, in conclusion, what I would like to tell you is that the uh, partially premixed flames are good because they are considered to be soot free. But that does not mean that there is no particulate in such flames. There can be nano-organic carbon particulates which are very small in their size, and they're so small that they do not behave as solid particulates. They behave more like liquid particles, liquid drops of very small diameter, less than 10 nanometer diameter. And when you measure them from different positions of the blue region, under all the circumstances, we found their existence in different types of flames with different equivalence ratio. And they are so fine that they do not emit or absorb visible wavelength light. The emission or absorption also always in the ultraviolet region, right? And they are hydrophilic in their nature, because of which they get absorbed. So these particulates present in the blue flames are also very harmful, in the sense that they are so small that they can penetrate deep into your body, and they can also affect the environment by controlling the absorption pattern of the environment, resulting global warming. So thus the message from this work, and there are other works. An Italian group, they have done this very extensively with different types of flames and also in engines. We also did this experiment in SI engines and found similar results. We normally say that diesel engines emit particulates, right? Because diesel engines really emit soot particles. And is for SI engine, we do not measure particulates because we think that SI engine, as in SI engine, premix flame is obtained, right? The fuel burns in the form of a premix flame. Particulates are not formed. So therefore, if you take your car for pollution test, your petrol car for pollution test, you will see that they measure hydrocarbon, carbon monoxide, and NOx, but not the particulates, because it is normally conceived that these petrol cars, petrol engines, as they burn the fuel in uh, in the form of a premix flame, soot formation does not occur there. So it is true that petrol cars do not form soot, and therefore they do not emit soot. But what we have found from our measurement, similar measurement in petrol engines, and other people also reported similar things, that though the petrol cars do not emit soot particles, but they emit these nano-organic carbon particles, which are the early form of soot particles. So they have different characteristic behavior from the soot particles, and therefore, if you use a soot measurement technique to measure them, you will not detect them, right? You will not detect them. So they will remain undetected, and they are so fine in their size that normal particle measurement techniques or particle measurement instruments will not be able to capture them, but they are present in the exhaust of petrol engines, as was found in our experiments and in experiments of some other groups as well. So this is what I wanted to tell you in this lecture. And these Bireshwar, actually he did most of the work on this item with me, and there are other groups also. Dipanjan and Rajashri were two master students who also did work on LPG flame, and Ranjan, as you know, is my colleague in the department, and we worked together when we did this work. Okay, so thank you very much. Uh, if you have any question, I will be happy to answer if I can.
Thank you, sir, for your very informative lecture. The floor is now open to any question from the participants.
So it is very nice to see that you're acknowledging your teammates. It's very humble of you, sir. You're acknowledging all your teammates
In
in your
fact,
research work.
in many cases, they actually do the work.
Yeah. So, since you're a person of our generation, so it is quite obvious that you have that kind of humbleness and that kind of ethics of acknowledging people who really assist. Now the situation has changed. I hope you will agree with me. Now, sir, one simple query that I have, like you have said, like in petrol engine, obviously there are particulate matters in very minuscule sizes that are still getting emitted. Sir, do you agree that in LPG also the same effect will be there?
Yes, yes. Actually, this measurement that we did was with LPG only.
Okay.
So yes. So in
So,
LPG stores also they will be emitted,
yeah,
not large in quantity, small in quantity, but when you
but
consider
still
them
it will be
together,
there,
I
na,
mean,
sir? But still it will be
yes,
there.
yes,
Like,
it will be there, right?
yeah. Now the people are, I mean, we are being told like if LPG is fitted in your car, less pollution. It is not like that actually. Those
Yes,
particulate matters
less
will be there.
pollution. particulate matter will be there, less pollution in many other sense. I mean,
Yeah.
if conventionally for cooking, people used to burn biomass in
Right,
different
sir.
form,
Right,
and
sir.
those burnings are highly polluting in nature
Right.
because they are incomplete, so they emit different hydrocarbons and carbon monoxide, and they also emit a large amount of particulates in the form of soot and also in the form of small ash, and they are large in quantity. When you burn LPG, there will be nano-organic carbon emission from LPG flame, but they are small in size, so that way they are harmful because they can penetrate deeper into your body, but the quantity of emission is much less, not that high. So that way the LPG flame is much cleaner
Yeah,
in,
sir.
into
I'm
if
not
you
talking about
consider
the
in
LPG that
totality
you're
much
using.
cleaner.
Sir, I'm not talking about the LPG that you're using for the house applications. I'm referring to the LPG fitted in the vehicles.
Yes,
Now it is
there
very
also.
common. Now it is very common in private and commercial vehicles. LPGs are being widely used as um, alternative to the petrol and diesel fuels. So I hope there is also an emission related to that, sir.
Yes, that is particularly related to emission,
Right, sir.
and that is for a different reason. That is because LPG will give less emission. I mean, it is not that LPG will give no emission. It is because LPG will give less emission compared to petrol or diesel.
Right, right,
This is because of the fact that LPG being gaseous can mix with air more homogeneously compared to liquid fuel. I mean, uh, in case of petrol, of course, petrol has a much higher volatility compared to diesel. And in case of petrol engine, you inject the petrol early in the induction stroke, right? So there is much time for the petrol to evaporate and mix more homogeneously compared to diesel. But if you consider LPG, LPG being gaseous can blend even more homogeneously compared to petrol. And that homogeneous mixing of the fuel and air will result in a cleaner combustion. And that is why LPG is said to have, I mean, said to give cleaner, I mean, less emission compared to petrol.
yeah,
And
sir.
they
Emission in terms of NOx, SOx, right? But the
not only in terms of NOx, SOx, but also in terms of carbon monoxide and hydrocarbons.
right, sir. But the particulate matters that you have just mentioned, it will always be there with LPG
It
also.
will be there with LPG also, but much less in quantity compared to diesel. And I mean, in petrol also, when we did measurement with petrol, we in the petrol engine we used petrol, and we found NOC particles to be there, and NOC particle also there in LPG. So it is not that LPG will give you no emission. It is
Right,
only that LPG will give you less emission compared to liquid
right,
fuel.
right, right, sir. Right, sir. But still, well, I mean, the carbon footprints will be at least lesser in terms of LPG that we are using.
No, I will not say that because carbon footprint is because of, I mean, even when you have carbon dioxide, it increases the carbon footprint. Footprint is because of any form of carbon in the atmosphere. Now, when you burn LPG, there is, even with cleaner combustion, you will have carbon dioxide formation. LPG also contains carbon, and so therefore there will be carbon dioxide formation. So LPG will not, I mean, give you any much benefit in terms of carbon footprint, perhaps. But again, if you can have a better efficiency with LPG compared to petrol, then probably will burn less fuel, and then you will gain a little bit in terms of carbon.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Any other question from any other participant? I guess there is no question. Sir, I
Okay.
have one question
Yes.
related to this. That you have mentioned that there will be particulate matters, and those particulate matters are typically order of magnitude smaller.
Okay. Shall I close the presentation?
Yeah, sure, sir. No problem.
Or okay.
So,
Let me close the
because
presentation.
the size of the
Hmm.
particulate matters is smaller, so we know that as the size becomes smaller, so it can penetrate more into the human body. So,
Right.
is there? Is there currently a thought is going on to build a framework so that we can assess its effect on the health? Because more and more,
Oh, not really. People have not started to work on these nano-organic carbon particles. This is perhaps because of the fact that the quantity of nano-organic carbon particles are less, even with petrol cars, and it is more difficult to, I mean, to um, to detect these particles because they are so small. If you have to detect them, you have to really get into very expensive and skillful measurement techniques, which are difficult to be done in common places, right? So that is why they are not yet been measured,
okay.
but probably in future sometimes they will be considered.
Yeah, so as the conventional cars are getting replaced by LPG and CNG, so I mean this study may be the need of the hour.
Yes. Yes, maybe. But nowadays people are talking about battery car.
Yeah.
So
Okay. Okay then. Any other question from any other participant?
Sir, if as your research goes, like if the particulate matters enters through the nose and goes into the lungs and through the areola and then diffuses into the bloodstream, so it's a really harmful threat to the human
yes,
health.
it is harmful not only for NOC but also for soot particles, because soot
Right,
particles are also very small in size. They
right,
may
sir.
not be able to cross the alveolar barrier, but they can go deep into the alveoli, and that is also not very good situation, because they will clog the alveolars, and
Exactly.
that is also very harmful.
And it gets into the bloodstream, it will always cause n number of problems to the human health.
Right, right, right. That is true.
So the emissions that are coming out from the power plants, I mean, from the exhaust of the power plants, maybe some particles may be of that the size of the shoot particles are emitting
No,
into the atmosphere.
not really, because from power plants, the particulates are mainly ash.
Yeah, maybe
In
the
case of
size of
power
the
plant,
particles
mainly
may
ash.
be, some of the particles might be as small as the
No,
shoot particles.
the ash particles are bigger in size. The ash particles are of PM10 or PM2 2.5 category, not even PM 2.5, PM10 category. But nowadays, with the introduction of ESPs are so efficient that the particulate in the flue gas coming out of the chimney is almost negligible.
Okay,
ESPs are 99.8%, 99.9% efficient.
right, sir.
Okay. Any other
Sir,
question?
sir,
Yeah.
sir,
Please.
I want to add one thing that sir, I'm from industry. So in our
Yes.
industry, we use boiler and also the diesel engine generator. And sir, in this regard, we have the soot blower also. That means you have mentioned that the soots are very harmful to the human body and the atmosphere also. So there is the provision is the blower, which is driven by the steam. So before going to the chimney or in the atmosphere, we did the blow up the soot by applying the steam. The soot blower is there. After that, it goes to the ESP, as you mentioned, and then it go to the chimney or stack.
Right. Soot blower, actually, it is called soot blower, but the steam in soot blower, or steam of soot blower really blows out the ash deposited on the water wall tubes, or maybe superheater tubes, right?
Right.
So they are called soot blowers, but they do not really blow soot. They blow ash from the surface of the tubes.
Exactly, sir. Exactly. Okay, sir. Thank you, sir.
Thank you.
Any other query? So I guess there is no other query. So in that case, let us thank Professor Datta for his very much informative lecture and the subsequent discussion. So thank you, sir, on our behalf.
Thank you very much.
Thank you,
Thank
sir.
you for inviting me.
Thank you, sir, for your wonderful presentation and lot of research information. It was very helpful and resourceful for us, and for the new generation researchers, it will pave an avenue to the new dimensions that you have shown through your research, sir. It was really wonderful presentation. I really appreciate the work you have
Yes,
done.
I will be happy if some of the younger people
Right,
carry
right,
on
sir. Right,
research
sir.
in this direction,
Right, sir.
uh,
This is kind of interaction
or
we
maybe
like
in
to.
any area related to,
Right,
I mean,
sir.
combustion and
So
emission.
this helps to expose our young generation faculty members to mop up ideas into the new avenues, like with the people and expertise that you people are having. So it always an inspiration to the young generation of faculty members to search for new ideas and pave new ideas into the research domain. So it's really wonderful, sir, having with us, and I really thank you for your expert lecture and your time that you have given for to us in this faculty development program. It is wonderful having you with you, sir.
Okay.
Thank you.
I'd like to
I also thank all
extend.
the participants to be with me
Exactly, sir.
for
I
the.
further like to extend, like if you have a time with us physically, we'll be contacting you, so that for
Yes,
an
that I will
for our
definitely
students
do.
also, this will be very helpful for our students. So I'd like to have an opportunity to have physically in our institute for a lecture, vis-a-vis lecture with our students, sir. It will be very
Okay,
helpful
that
for
I will
them.
do. I will do sometimes. Not
Right,
this
sir.
lecture,
No,
but
no,
maybe
no.
something
We'll
more
discuss
fundamental
that.
for the
We'll
students.
discuss that. We'll frame up some events so that you can drop down to our place and have a vis-a-vis interaction with our students. It will be very helpful and resourceful for the young generation students, sir.
Okay. Thank you.
Thank
Thank
you,
you, sir.
sir. Nice to have
Thank
you,
you.
Thank you,
sir.
sir.
Thank you.
Thank
Thank
you.
you,
Good
sir.
night, sir. Good night.
Bye. Good night.
Thank you. Uh,
Okay.
we also like to thank Atal AICTE for sponsoring us. And this lecture series will go on. So tomorrow we have another invited speaker. So be on time and please make sure you fill in the feedback form that is given in the chat box. Thank you all and good night.
Thank you. Good night.
Thank you,
Good
sir.
night, sir. Good night. Good
Good
night,
night.
everybody.
Good night.